Hello students, welcome back to my YouTube channel PD Tutorial, and today in this video I am going to solve some problems based on Green's theorem, and I have also uploaded the proof of Green's theorem. You may check the description box for the link. It is provided there, and let's start with the few examples. Okay. So the first question is, verify Green's theorem in the plane for line integral this where C is the closed curve of the region bounded by the line and the parabola. Okay. So we have to solve this line integral and verify the Green theorem, okay? That region is bounded by this line, straight line, and by the parabola along y-axis, okay? So I have drawn the figure here. This is the equation of line, that is y equals to, and this is the equation of parabola, this is y equals to x square. If you solve this equation, you find that point of intersection is origin, and this is 1, 1. Coordinate is 1, 1. Just give it name P. This is origin, so denoted with O. Write M here. This may be L. Okay. Now, solution. Given line integral xy plus y square dx plus x square y. I am going to solve it with proper theory, okay? So you will understand how to write it for the university exam, okay? And where capital C is the closed curve of the region bounded by the line y is equals to x and the parabola y is equals to x square. Now comparing with line integral m dx plus n dy. I hope you know the formula. This is written for the Green's theorem. Line integral m dx n dy. This is the format. So we are going to compare our line integral equation with this. We got m is equals to what? Xy plus y square. Xy plus y square, and in place of n it is written x square. So n is equals to x square. Now we are going to find del m upon del y, because according to the Green's theorem we have to find the value of partial differentiation with respect to y. So we get what? X plus 2y and del n, partial derivative with respect to x, we get 2x. From Green's theorem we know what? Surface integral r del n upon del x minus del m upon del y dx dy is equals to line integral m dx plus n dy. This is the formula. We are going to put the value here. Del n upon del x is 2x, and the value of del m upon del y is minus x minus 2y. Dx dy is equals to line integral. Write the integral directly, which is given in the question, x square dy. Surface integral x, after solving we get x minus 2y dx dy is equals to line integral xy plus y square dx plus sxy dy. Now we are going to put the limit here. So now we have to find the limit here. So take the stripe parallel to y-axis, okay? So if you see, the x-axis runs from 0 to 1. If we take the coordinate from here to here, for this closed region, we find that x-axis runs from 0 to 1, okay? And the y-axis runs from here to here. So the lower limit will be the equation of that parabola, that is y is equals to x square, and upper limit for y is equals to x, which is the equation of line. Now x runs from 0 to 1 and y run from x square parabola to line. Write it separately. X dx dy minus 2 double integral x is equal to 0 to x is equal to 1, y is equal to x square to y is equal to x, y dx dy, and this line integral same. Okay, now let's solve the double integral. Now we are going to solve it for y first. So the integral y is equal to x square, y is equal to x dy ds, we can write it as like this, minus 2 x is equal to 0 to x is equal to 1, integral y is equal to x square, y is equal to x, y dy dx. Okay, now solve it. Integration is y, after putting the limit we get x, creating this we get y, after putting the limits we get x minus x square, this is dx. Again solving this, we get y square upon 2, so write the constant outside. Okay, y square, after putting the limit we get x square x to the power 4 dx. So cancel it out. Now we are going to integrate this. After multiplication we get the separate integration of each term. I am going to write it directly because it's very easy. Upon 4, put the limit from 0 to 1, and for this we get x cube upon 3 minus x to the power 5 upon 5, 0 to 1. What we will get? 1 upon 3 minus 1 upon 4 minus 1 upon 3 plus 1 by 5. After solving we get minus 1 by 20. So this is the one part. So this is, we just find the surface integral. Now we are going to verify the Green's theorem by proving that if we solve this line integral we also get minus 1 by 20. So LHS is equals to RHS. Now this line integral xy plus y square dx plus x square dy is equals to, so how to solve the line integral? Solving line integral we take this line first, this curve or line, what you can say. So we take that curve first. So this is the curve. The equation of this curve is y is equals to x square because this is the part of parabola. Secondly, we are going to solve for this line. This is the straight line y is equals to x. So we are going to find the line integral in two parts. First for this and second for this. Integrate first OLP. First we are going to solve OLP and second we are going to solve OMP. OLP xy plus y square dx plus x square dy plus PMO xy plus y square dx plus x square dy. Okay. For solving this we are going to put, for this line OLP, the value of y is equals to x square. So we are going to put the value of y equals to x square in the whole term for this integral. Okay. And for PMO, we are going to put the value of y equals to x in the second problem. So we get integration OLP x y equals to x square plus y square x square to the power x square dx plus y dy plus angle P, integration PMO, this is x square dx plus y square dy. Solve it. OLP, this will become x cube x4 dx plus y dy. This is PMO, this is 2x square dx plus y square dy. After solving we get 4 to the power 4. This is very easy integration, that's why I'm writing it directly. 2x cube upon cube 0, this is 120 plus y cube upon 3 12. So I put the limits here. So how to put the limits for x and y? Okay, so if you know from the Green's theorem, we take any closed region in the anti-clockwise direction like this. Okay, so if we start from this, so the x-axis will change from 0 to 1, okay, and y-axis change from 0 to 1 for this line. If we take this integral, okay, PMO, anti-clockwise direction, so x changes from 1 to 0 because it is moving in this direction because of anti-clockwise. So it changes from 1 to 0 and y-axis changes from 1 to 0. After putting, we get minus 1 by 20. Okay, hence the theorem is verified. So this is the homework for your practice. So with the help of Green's formula, you have to compute this line integral. Okay, you have to find the value of this line integral using Green's formula. So I will give you one hint. You will find that this is what? This is m and this is n. You will find the partial derivative for the Green's formula and find the surface integral. And you got the value for this line integral too. So answer is 1 upon 3. If you got the answer, please comment down below. If you find any query, please tell me in the comment box. Second question is find the area of the loop of Descartes' folium, which is the equation. This is the equation of folium x cube plus y cube equals to 3axy. This is the graph for the Descartes folium. Okay, this is the equation. So we have to find the parametric equation first. Parametric equation. This is the important example of Green's theorem. It is mostly asked in university exam. Folium. Okay, we have to put y is equals to tx in the equation. We get x is equals to 3at upon 1 plus t cube, and after putting x, the value of x in this equation, we get y is equals to 3a t square 1 plus t to the power cube. Now we have to find dx. We got 3a 1 minus 2 to the power cube 1 plus t cube whole square dt, and dy is equals to 3a 2t minus 2 to the power 4 1 plus t cube square dt. Now we have to find the area of loop. So this is the corollary of Green's theorem, one of the corollary, that area of loop is given by, this is for folium only. Okay, you will remember that area of loop is given by half line integral x dy minus y dx. Okay, this is the formula. So you already find the value of x and dy dx each. So put it. This is 3at 1 plus t cube 3a 2t minus t to the power 4 1 plus t cube whole square. Now the value of y 3at square upon 1 plus t cube, and dx will be 3a 1 minus 2 to the power cube 1 plus t cube whole square. Okay, after solving we get half. Put the constant outside. This is 3c9 and this is a square. Here 9 and a square. Take this out as a common. You get t square plus t to the power 5 1 plus t to the power cube ka cube. Okay, so after solving this you get that result. Okay, I am doing the integration part fast, and this is only the easy calculation, nothing much. 9a square upon 2. After taking common square, we get 1 plus t cube. This is 1 plus t cube. Cancel out, it will become square. 9a square upon 2. This is t square 1 plus t cube whole square. Put 1 plus t cube is equals to u. This will become 3t square dt is equals to du. You get 9a square upon 2 du upon u. So this is u square. So I have made a mistake here. 3a square, this is u, this is 1 upon u. Okay, after solving this integration, we got 1 upon u, 3a square upon 2, 1 upon 1 plus t cube. This is 0 to infinity. After solving, we get 3 upon 2a square. Okay. So the next question is, a vector field F is given by sin y I cap plus x1 plus cos xy. Sorry, this is cos y j cap. Evaluate the line integral this, where c is the circular path given by this equation of circle. So the center is 0, 0 and the radius is a. The format is given here. Line integral is equals to f dot dr. So what is f? It is given here, sin y I cap plus x1 plus cos y j cap. And what is dr? So I have already make you understand what is the value of r vector and what is dr vector. If you haven't seen this video, please check the description box. Link is provided there. R vector is equals to xi cap, yj cap, zk cap. Dr vector is equals to dxi cap, dyj cap, and dz is equals to dzk cap. So put the value here. This is dxi cap, dyj cap, dzk cap. After this, we are going to find the dot product of each term. We get sin y dx plus x1 plus cos y dy. That this is the m and this part is n. Now it is visible. So we have to find del m is equals to del x, the sin y. We have to find del m upon del y. So we get minus cos y, and del n upon del x, we get 1 plus cos y. Put the value, line integral sin y dx plus x 1 plus cos y dy is equals to surface integral del upon del s x 1 plus cos y minus del upon del y sin y. Put the value, double integral 1 plus cos y minus cos y dx dy. This got cancelled. We get double integral dx dy. So we have to find the surface area of circle. So area of circle is pi r square. So we can write it as pi r square. What is radius here? I already make you understand. This is a. This is a ka square. So this is pi a square. Proved. This question is the homework. If you got the answer, please comment down below. If you find any query, let me know. Answer is 3 upon 2. Okay. Question is, verify Green's theorem in the plane line integral x square plus xy dx plus x square plus y square dy, where c is square formed by x is equals to plus minus 1, y is equals to plus minus 1. So I have already drawn the figure here. So this region is bounded by the line x is equals to plus 1. So if you draw the line x is equals to 1, it is like parallel to y axis at coordinate 1, 0. Like that we draw y is equals to 1, x is equals to minus 1 and y is equals to minus 1. So this is the region bounded by this line. So we have to, with the help of Green's theorem, we have to solve this line integral. So let's start. Firstly, it is already mentioned the line integral. So this is m and this is n. Okay. So you have to find del m upon del y and del n upon del x. So this line integral x square plus xy dx plus x square plus y square dy is equals to surface integral. What is the limit of x-axis? X-axis is changing from 1 to minus 1. 1 to minus 1. So here we are going to take the direction in anti-clockwise direction. It is already discussed in the Green's theorem video. So we have taken the limit of x is from -1 to 1, -1 to 1, and y is equals to -1 to 1, -1 to 1. Then we have to put the value of del m upon del x, that is x square plus y square minus del upon del y, x square plus xy. Solve it. We get -1 to 1, -1 to 1, 2x minus x. Okay, after doing partial derivative, this is dx dy is equals to -1 to 1 x, -1 to 1 dy dx. This is -1 to 1 x. This will become dx. Solving this, we get x square upon 2 -1 to 1. This will become 0. So the surface integral becomes 0. Now we are going to solve the line integral, and we have to prove that LHS is equals to RHS. From the figure, we have to solve the line integral part-wise. Like first we are going to solve it in an anti-clockwise direction, and start with the 1 by 1 line, like along AB. Then we integrate along BC, then CD, and then DA. After that, we get the summation of all four, and we find that the whole integral of that contour C. So look here, along AB. If you see along AB, the coordinate x is equals to 1, that is constant, it is not changing, so dx is equals to 0, and the coordinate y is changing here. See, -1 to 1, so y is -1 to 1. So we are going to put the value along AB, f dr is equals to, what is the value of y? -1 to 1, -1 to 1. Put the value of line integral. If we see this line integral, that dx is 0, so this part becomes 0. Value of x, that is 1, that is constant, and y square is varying. So we are going to solve it. After integrating it, we get y cube upon cube -1 to 1. The value is 8 upon 3. Okay. Again we are going to solve in the anti-clockwise direction along BC. So here the coordinate of x, is changing 1 to -1, and the coordinate of y is constant. So along BC, the coordinate of y is 1, so dy is 0, and coordinate of x is changing from 1 to -1. So put the value in integral f dot dr, that is x is equals to 1 to x is equals to -1. Now from the line integral you can see the value of dy is 0, so this part will become vanish, and we will only solve for this part. So y is constant here, so we put the y is equals to 1 here. You get x square plus x dx. After solving, you get the value 2 upon 3. Likewise, if you solve for CD, the value of x is same, x is equals to -1, so dx is equals to 0, and y is varying from 1 to -1. Along CD, x is equals to -1, so dx is equals to 0, and y is varying from 1 to -1. So integrating along CD, f dot dr, -1 to 1, 1 plus y square dy, we just put the value of x is equals to -1 in the line integral, it will become -8 upon 3. Likewise, we solve along dA, we are doing in anti-clockwise direction. Don't dare to do in the clockwise direction, okay? This will be wrong. So in CD, we are solving for dA. the coordinate y is still, so y is equals to -1 and x is changing from -1 to 1. So y is equals to -1, so dy becomes 0 and x is varying from -1 to 1. Integration -1 to 1 x square minus x, by putting the value of the y is equals to -1 and dy is equals to 0, we get 2/3. Now to find the whole integral, to find the whole f dot dr, we have to add AB f dr, BC f dr, line integral CD f dr plus line integral dA f dr. Write the value 8/3. So this is -2/3 minus 8/3 plus 2/3. This will become 0. So if we find the value through line integral or surface integral or via surface integral, the value is 0. So the Green's theorem is verified here. So I hope you don't find any difficulty. I tried my best to make you understand the example based on Green's theorem. If you like the video, please hit the like button. Don't forget to subscribe my channel and press the bell icon for further notification. Thanks for watching this video.